Today, we're going to look at something that could, and I mean really could, change technology forever. It's a new fractal structure. It's called the Perez Hourglass, and the claims around it are just huge. We're talking about solving some of the biggest problems in computing. So, yeah, let's get right into it.
So here's a wild thought for you. What if the key to the next generation of computers wasn't in some high-tech lab, but was actually hiding inside a pattern you probably learned about back in high school? It's a pretty bold idea, but by looking at something familiar in a totally new way, we might just unlock a whole new mathematical universe.
And there it is. This is the Perez Hourglass. You can see right away, the top part looks super familiar, right? That's Pascal's triangle. But the bottom half? That's something else entirely. And according to the people behind it, this isn't just a pretty shape. Nope. They're saying it's a blueprint for things like unbreakable codes, perfect AI memory, and even quantum computers that can't fail.
So you have to be asking, where did something this revolutionary come from? Well, believe it or not, the answer has been sitting right there, hiding in plain sight for more than 350 years. It was tucked away inside one of the most famous patterns in all of math, Pascal's triangle. You know, we all learned that Pascal's triangle is built using simple addition. But what if you flip that idea on its head? What if you built a mirror image of it, but based on subtraction instead? Well, that one little twist, that's the key that opens the door to the hourglass.
So let's actually look at how you get from a simple triangle to this incredibly complex shape. The way you build it is actually surprisingly simple, but the thing you end up with is anything but.
It's basically a three-step recipe. First, you've got the northern hemisphere, which is just your good old Pascal's triangle. Then you stick a single point right in the middle. That's the waist. And then you generate the southern hemisphere, which they call the antimatter twin, and you build that using a subtraction rule. This table just lays it out perfectly. Look at row 4. In the north, with addition, you get that familiar 1, 4, 6, 4, 1, but down in the south, using subtraction, you get something totally different. 1, 0, 2, negative 2, 1. It's the same basic idea, just inverted, and it opens up this entirely new mathematical landscape. Now, this structure isn't just a cool-looking doodle. It turns out it's governed by a set of 6 fundamental mathematical rules that just pop out of it naturally. And these principles are what give the hourglass its almost magical properties. And the properties are just astounding. You have famous things like the Fibonacci sequence just showing up on their own. Every single row in that antimatter southern half adds up to exactly 2. And get this, if you color in the even and odd numbers, you get these perfect mirrored images of the famous Sierpinski fractal. It's like this grand unification of all these incredible mathematical ideas in one single shape.
But okay, out of all those cool properties, there's one that really stands out from the crowd. The source material calls it Theorem 7, and it's basically described as the golden key. It's the thing that turns this beautiful fractal into an actual powerful tool for computation.
I mean, this quote from the research just nails it. Theorem 7 is what takes the hourglass from being a cool thing for mathematicians to study and turns it into a blueprint for a machine, a deterministic, computational substrate. So what in the world does it actually prove?
Okay, here's the absolute heart of it. Theorem 7 proves 2 critical things. First, something called parity preservation. It means if you could fold the hourglass in half, any number touching its partner will always have the same parity. They're either both even or both odd. But second, and this is the real game changer, global uniqueness. Every single one of those pairs of numbers that touch is completely unique. The pair, say 6, 2, shows up exactly one time and never, ever again, anywhere in the whole infinite structure. And this isn't just a hunch. They've put this to the test on a massive scale. Researchers have computationally checked this property for 2.5 billion unique pairs of numbers. That's just a staggering amount of data to verify. And this number just says it all. Out of those 2.5 billion checks, how many times did the rule break? How many violations did they find? Exactly 0. That kind of mathematical perfection is the bedrock for everything else they claim this thing can do. All right, so we've got this mathematically perfect structure where every location has a unique built-in address. What can you actually do with that? Well, this is where we turn the corner from pure math to some pretty world-changing applications in quantum computing, cryptography, and AI.
Okay, first up is a huge one. It's an application that tries to solve a problem that has been holding back the entire field of quantum computing. You see, the biggest headache for quantum machines is that they're constantly making errors. The hourglass, its creators claim, has a natural, built-in solution for that. So on the left, you've got the issues with today's quantum codes. They're incredibly fragile, they're inefficient, but on the right, you see the promise of the hourglass. Its fractal geometry is said to naturally just drain errors away, creating this sort of self-healing quantum fabric that could dramatically outperform anything we have now, and maybe even break long-held theoretical limits.
Next application, data security. With quantum computers on the horizon, there's a real threat they could break most of the encryption we rely on today. But the unique, totally unpredictable pattern of numbers in the hourglass could provide a new foundation for what we call post-quantum cryptography. So because every single pair of numbers is unique and never repeats, the hourglass can basically act as a source for an infinite secret key. That's the basis for something called a one-time pad, which is literally the only truly unbreakable form of encryption that exists. It also opens the door to new ways of securely exchanging keys and creating digital signatures that even a quantum computer can't crack.
And this final application might be the most mind-bending of all. It's a new kind of architecture for what's called associative memory. Think of it like this. It's memory that works more like a human brain, finding information based on what it is, not where it's stored. And that is absolutely crucial for building smarter, more efficient AI.
They call this architecture PAM, for Perez Hourglass Associative Memory. Because every single spot has its own unique numerical address, it promises a system of infinite, error-proof memory that can pull up information instantly, even if you only give it a messy or incomplete clue. It's a model that could, seriously, leave every other approach we have in the dust.
So when you kind of zoom out and look at the big picture, the Perez hourglass starts to look like more than just a clever trick. It really presents itself as this fundamental pattern that ties together all these different fields of math and even seems to mirror structures that we see out in nature.
I mean, just look at this list. You're talking about the titans of math history here. Pascal, Fibonacci, the golden ratio, Sierpinski. The hourglass is being presented as this one place where all of these monumental ideas seem to meet and connect, which suggests it could be a really deep, fundamental blueprint of our mathematical reality.
And that just leaves us with this final, really powerful idea. You know, we think of an hourglass as a symbol of time just slipping away. But here, that same shape is transformed. It's not passive anymore. It's active. It's a structure that computes. Which really just leaves one question. What will we compute with it?